In this video, we are going to study continuous probability density functions. Let's start by recalling discrete random variables. We have probability mass functions related to discrete random variables. Now, overall, one unit of probability is assigned over all possible values of our discrete random variable x. So if we are looking for probability of random variable x lying in some interval from a to b, then we have to sum over all values of our PMF where small x lies in interval from a to b. We also have that all values of probability mass function are positive. And in that particular case, when we are working with discrete random variables, those values of PMF can be considered as point masses sitting on top of possible values of random variable x. So if we are looking for specific value of random variable x, let's say being equal to some value c here, then we can look at a graph of PMF, and the value on y-axis is going to exactly represent probability that our random variable x is equal to c. Now, when we are working with a continuous case, we will have a function that is known as probability density function, or short for PDF. For continuous random variables, we also have one unit of probability distributed over all possible values of random variable x. However, as opposed to discrete case when our PMF might be considered as point masses, in a continuous case, our graph for PDF is going to look like a continuous line. Then, if we are looking for probability of random variable x lying in some interval, let's say from point A to B, then we have to calculate an area under our probability density function. Now, to find an area under a graph of some line, we have to integrate. So if we are looking for probability of random variable x lying in interval from A to B, we have to find an integral of PDF of our probability density function from x equal to A to point x is equal to B. Now, our PDF line is not necessarily uniform, meaning that we have more density in some parts of region as opposed to others. Now we have similar conditions as for probability mass function for discrete case. First, the values of PDF should be also non-negative. And in a case when working with discrete random variables, the sum over all possible values of x of our PMF was equal to 1. So 1 unit of probability is assigned over all possible values of x. We'll have a similar condition for continuous PDFs. Now, our x, it is a fact that our x, which is a continuous random variable, is going to all possible values of our continuous random variable x is going to lie on the interval from -infinity to +infinity, meaning that an integral from -infinity to +infinity of PDF of x should be equal to 1. So 1 unit of probability is assigned over all possible values of x. You might consider this as 1 kilogram of snow falling over all possible values of x. Which brings us to the following definition of continuous random variables. A random variable is considered as continuous if it can be described by a valid PDF. Probability density function satisfying the following conditions. Now, so for a random variable to be continuous, it is not enough that it takes on numerical continuous values. It also should be described by probability density function. And if we are looking for probability of more complex intervals, let's say probability that our random variable x lies in interval from a to b, or on interval from c to d, then we, using additivity property, we can split that into the sum of the following two probabilities, which we can calculate by finding an area under the following two intervals. Let's say our interval from A to B is over here. First, we have to find an area under that interval. Then we have to find an area under an interval from C to D and sum those two. Now let's take a look at the further properties of probability density function. Let's say we are looking for probability that our random variable x lies in some small interval from a to a plus delta, where delta is a small positive value. Then probability that our random variable x falls in that interval is defined by the area under our PDF curve over an interval from a to a plus delta. In the case when delta is small, we can replace that area under our PDF curve by an area of the following rectangle that has a width of delta and a height of PDF at point A. So probability that our random variable x is in that interval is equal to PDF at point A multiplied by delta. So if we express PDF in terms of that probability and the width of our interval, from which we can say that PDF here is described as probability over unit mass, from which we have a name of our probability density function. So probability density function describes a density. Let's see what happens if we are looking for probability that our random variable x is equal to particular value a. So probability that random variable x lies in interval from a to b can be described as an integral from a to b of PDF of x. Let's see what is going to happen if we replace b with a. Then this is probability that x lies in from a to a, or probability that x is exactly equal to a. So replacing upper limit of our integral, we'll get an integral from a to a of PDF function, which is equal to 0. So probability of our random variable x being equal to particular value is equal to 0. However, infinite union of such points in some particular interval is going to give us some positive probability, which is not surprising. This is similar to the case when a single point has a 0 unit length. However, infinitely many union of them on some interval is going to give us some positive length.